Welcome to my dear students. Here we'll go with the next example. Which of the following is more readily attacked by electrophile? So that they have given a nitrobenzene, benzoic acid, benzaldehyde and even phenol. Here what happens is, if the multiple bonded group is present with the compound, it would not be act as a electrophile. It drags the bonded pair of electron and acting as a nucleophile. So in a nitrobenzene, a nitro group attached is electron withdrawing group. In benzoic acid, that carboxylic acid group is also electron withdrawing group, and even benzaldehyde, which contains an aldehyde group. I will tell you, see the structure of all these things. So in a nitrobenzene, where the coordinate bond between nitrogen and oxygen, this is a nitrobenzene. As per the second option is concerned, this is the benzoic acid, where the benzene is binded to the electron withdrawing group. As I already told you, multiple bonded groups are electron withdrawing in nature. These are electron withdrawing nature. So this group will experience the electron withdrawing sense with respect to benzene is concerned. So that this comes under the resonance, where the bonded pair of electrons are shifted here, and what happens is this bond will come here. So like that, there is a conjugation takes form, and this is the benzoic acid. As per the third option is concerned, again the same thing, where the benzene is binded to electron withdrawing group again, because multiple bonded groups are electron withdrawing in nature. Bear that in mind. And last thing is the phenol, where benzene is binded to hydroxyl group, which is electron rich, tries to donate a lone pair. So if it tries to donate a lone pair, what happens is the electron donating orientation effect will cause the electron rich density over 2 ortho and 1 para position. Here what happens is electron withdrawing. Electron, we tell like electron withdrawing groups attached to benzene will direct the incoming electrophile to meta position, electron withdrawing group directs the electrophile to meta position, where there is only one meta position is there. Only one meta, since there are two meta positions are there, but in resonance the position of them is considered to be 1, so that product formed is only 1. But in case of this phenol, what happens is this is an electron donating oxygen is there, because it's an electron rich center, so that electron donating groups, this comes under the resonance. Okay, so electron donating group attached to benzene will direct the incoming electrophile to ortho and para positions. If you compare these two lines, like electron withdrawing group, electron withdrawing group, electron withdrawing group, electron withdrawing group, there are three options are there with electron withdrawing group, and this is only contains electron donating group. So that here there is a possibility of electron withdrawing group, means this is minus M effect, this is also minus M effect, this is also minus M effect, but this is plus M effect. What happens if the plus M effect is present? This makes two positions available for the electrophile attack, but these make only one position, that is a meta position, for the availability of the electrophile to attack. So that here with these two notations will have the possibility of attacking the electrophile to ortho and para positions. Okay, we'll discuss these orientation effect in detail by taking many of the examples. Okay, here we'll go with orientation effect in order to know electrophilic substitution and nucleophilic substitution. The effect of the substituent. The effect of substituent attached to benzene on electrophilic substitution and nucleophilic substitution. Let us talk on to this particular point. Why I am talking about this thing is many students will get confused with plus M effect and minus M effect. They will not understand the effect of substituent on the electrophilic attack towards the benzene ring and nucleophilic attack towards the benzene ring. That is what I have taken a break with that PPT, and I am extending this concept because this has more importance in upcoming classes like second PUC and even those competitive exams. So let us talk on that. Here we will have one benzene attached to, let us suppose, alkyl group. We know that alkyl groups are always electron donating in nature. They donate the electron towards the benzene ring, and this is a substituent now. This is the substituent, and we need to know about its orientation effect. The incoming electrophile or the nucleophile. I already told about these things. This is the electron deficient center, this is the electron rich center. So that in order to attack to the benzene, these species have 1, 2, 3, 4, 5 possibilities are there. So in all those 5 positions, which position these electrophile nucleophile will choose? So that is called as the orientation effect. The existing substituent will orient or will direct the incoming electrophile to or incoming nucleophile to the positions, certain positions, and that position will be decided by only this substituent. So that effect of substitution, effect of substituent on the substitution of electrophile and nucleophile with the other positions of the benzene is discussed right now. So what happens if the electron donating group is there? Here the electron donating group, I will write, this is methyl group is the general example. If I take electron donating group, so what happens, I will tell you. See, here there may be alkyl groups like methyl or ethyl, you can take any of those alkyl groups. They are electron donating in nature, and the groups which the groups or the atom or a group of atom or group of atoms attached directly to benzene should have a lone pair of electrons. lone pair of electrons. It may contain one lone pair, it may contain two lone pairs, so it may contain three lone pairs of electron. So that will be called as electron donating group. Alkyl group I have already represented right over here. You can take the halogen, which contains one as a bond pair. I will show you, like now benzene, if it is attached as a halogen, let us suppose fluorine, chlorine, bromine and iodine, they contain a lone pair and they tend to donate a lone pair of electron, not as much as other groups, but it's a slightly deactivating group. Okay, it is not that much activating group. So electron donating groups are called as activating groups. Activating group for the electrophile, because on donating the lone pair of electron, what happens is the benzene ring becomes electron rich center, so that electrophile will easily go and attack that benzene in certain positions. I will tell you what is the idea behind the selection of the position. So that the activating groups are electron donating groups which activate the position of that carbon for the electrophilic substitution. So electrophilic substitution activating group are nothing but electron donating groups. And this is the halogen attached to benzene ring is an example, and you can take the NH2 aniline highly activating group, and even the OH group attached to that, or you can take the ether group. So that here the halides attached to them, or the halogens attached, or you can take the hydroxyl group, or you can take the alkoxy. I have taken the methoxy right over here. You can take alkoxy. In general, you can take it as RO. Okay, and even the highly activating groups such as single bond NH2 you can take. So here the first topic, halogens, halogens, and the first topic of organic section, which is a halogen, and phenols and ethers. After that we go with the now the point comes with the aldehydes, ketones and carboxylic acids. Here what happens is the benzene attached to electron withdrawing group. Electron withdrawing group. What are electron withdrawing groups? Electron withdrawing groups are the atom or group of atoms. Mostly it's a group of atoms. Atom examples are less here. A group of atoms examples are more here. I will tell you, see here. As I already told, electron withdrawing groups. Electron withdrawing group contain a multiple bond attached to carbon which is binded to benzene ring. So the benzene ring, the carbon binded to benzene ring should contain multiple bond with the oxygen or multiple bond with the nitrogen, or the multiple bond like between, we can't have the multiple bond between the halogen. Multiple bond between the oxygen is possible, double bond is there. Multiple bond between nitrogen is possible. It contains a triple bond. Okay, so that the thing goes like that. You can take the carbon to carbon also. There is a double bond. So possibility. The only thing is it should contain a carbon binded to benzene should contain a multiple bond. So that I will take the aldehyde, benzaldehyde is an example of the whole example of that. And if you take a ketonic group, let us suppose acetophenone. This is a benzaldehyde. This is a acetophenone. It's a ketone kind of a compound. And if you take this example, let us suppose this is the benzoic acid. So aldehydes, ketones and carboxylic acid aromatic aldehyde, aromatic ketone, aromatic carboxylic acid. And as I already told, you can take, this is the electron withdrawing group in general, I am taking this as. So, electron withdrawing groups can be C double bond OH, that is aldehydic, C double bond O R, that is ketonic group, C double bond O OH, that is a carboxylic acid. You can take C double bond O NH2, that is a amide, and you can also take the C double bond O OR, that is ester kind of a compound. And moving onwards, cyanide is also attached with the benzene, also contain the multiple bond, which nitrogen is dragged a bonded pair of electron, and that gives the electron capacity to that group, cyanide attached to the benzene. So that these are the examples. If you look into the electron, donating groups, they will come the alkyl groups and halogens, even the hydroxyl groups like that. You can take NH2 group also, that is a amine, primary amine group attached to the benzene. They are called as primary aromatic amines. Okay, so these stay as an electron withdrawing group. You remember the point? If you flip this W in opposite, like if you have the mirror image of this, you will get the M. So that electron withdrawing groups are multiple bonded groups. Okay, the electron withdrawing group attached to the benzene should contain the carbon directly attaching to the benzene should contain the multiple bond. So that multiple bonded groups will direct the electrophile. Let us suppose electron withdrawing groups are those which contain multiple bond which direct the electrophile to meta position. This is the thing you need to know. Okay, I am telling you the trick that electron withdrawing groups attached to the benzene will direct the electrophile, incoming electrophile, to meta position, and they contain multiple bond. So that you can take like electron withdrawing group, they contain a multiple bond attached to that carbon which is further bonded to benzene, and they should direct the electrophile. They have the nature to direct the electrophile to that meta position. This is the trick you need to remember. Okay. Now coming to the their resonance. Resonance structures. Then only, if you know the resonance structure of them, then only you will catch the idea of how they direct the electrophile and nucleophile to ortho, para, and meta positions. In order to know that orientation effect by the substituents on the electrophile and incoming electrophile and nucleophile, we need to know about their resonance structure. See here. The resonance structure, I am taking the example of electron withdrawing group OH. You can take the any of the example that I have already listed in a previous explanation. So here I am taking the hydroxyl group. You can take amine group attached. You can take halogen. You can take alkyl groups attached to them. Here what happens? You can take the alkoxy group as well. Here they donate lone pair. So on donating lone pair, what happens is there are 2 electrons in this pair. Here, this is a benzene. Here there is a OH group. There are groups like this, and the structure of benzene. This is the kind of structure. If the lone pair is donated towards this bond, what happens? One electron. Now only one pair will remain with that. One pair goes as like this. So one electron remains with oxygen, one electron goes with the carbon. So that there will be the double bond between carbon of a benzene and oxygen of a hydroxyl group attached. So that oxygen will be electron deficient because of donation of only one electron. No doubt, it has donated 2 electrons, but 1 electron is remained with oxygen, only 1 electron is donated towards the carbon. If you write like this only, compare this structure and this structure, there is a positive charge, this is also positive charge, but here there is a negative charge, but there is no negative charge over here. If you write like this only, it is not a resonance structure, because a lone pair is converted into bond pair. Now this bond pair should convert into lone pair. Why? I will tell you. See here. This is the carbon. Now count the number of bonds with that. 1, 2, 3, 4, 5 are there, but the valence of the carbon is 4. So this should not happen in the resonance. What happens? This bonded pair is converted into a lone pair. So that what happens? One electron is gained by the oxygen, and this electron will go to the carbon which is present at the ortho position of this carbon. You know that if the substituent, immediate positions to a substituent will be named as ortho positions. The substituent, the positions next to ortho positions are called as meta positions, and that position which is opposite to substituent is called as para position. Here there is no necessity like the substituent should be there in only this position. Sometimes this also happens. Let us suppose this is a benzene where the position of substituent may be also present at this position. Let us suppose here there is a hydroxyl group. I told you the substituent present carbon, immediate carbons will be orthocarbons. After that, meta. The opposite to that will be para. Wherever you can take this OH group here also, no doubt. So these two are called as, at that point, these are called as ortho. This is a meta, this is meta, and the position opposite to this substituent is called as para. So this is the way how they have named the ortho, meta, and para positions. And the substituent present group present position is ipso position. They take like that. So here one carbon is there, here also one carbon is there. Sorry, here also one electron, here also one electron. There are 2 electrons are there with this bond. Now this carbon has a 5 bonds. In order to balance the valency, what happens? This bonded pair is shifted to here. Bonded pair means this carbon lose 1 electron. Here 1 electron is gained by oxygen, 1 electron is lost. So there is no change in the electron transfer for the carbon. It has gained 1 electron and it has left 1 electron to ortho position at carbon. So here also 1 electron, there goes. So what happens is there are 2 electrons gained by that carbon, in which one is of that carbon only and one is of that first carbon. Okay, so that it becomes a negative charge here, negative charge with a lone pair. One is of this carbon, one is of this carbon. So that second carbon's electron is this, and second, you can take like that, second carbon, you can take one of them as a second carbon electron and one is of first carbon. So that the structure is like this now. Then in order to balance the valency again, what happens is this goes resonating with this bond, and the lone pair now converted into bond pair, and bond pair of the bond between the third carbon and fourth carbon will move on the fourth carbon as a lone pair. And again, if it donates, what happens is the ortho position. Here, if you see ortho position, I have told you opposite position is para. So ortho position, para position, and ortho position are electron rich now. I told you if the electron is a negative charge, if the electron is present, it's a negative charge, nucleophilic. These are 2 ortho positions and 1 para position are nucleophilic centers now. So that if you are interested to attack the electrophile, let us suppose the electrophilic substitution is there. Electrophile is a electron deficient species and that attacks to electron rich center. So that since two ortho positions are equivalent, we will consider formation of only one product right out there. And for para position, so only one para position is left. In two ortho positions, we'll consider only one product, and in para position, we'll consider one product. So there are two products formed in which one is ortho substituted and other one is para substituted. In strong substitution, what happens? There is a substitution at this position also, and this position also. So becomes it's a tri-substitution in strong electrophilic substitution. You know all those examples for the tri-substitution. If only one substitution occurs, two ortho positions are considered as equivalent position, and there is only one product formation takes place, and this opposite position will be one product. So that there are for electrophilic substitution for electron donating group, if the electrophile is going to substitute, what happens? It directs electron donating group directs the electrophile to ortho and para position. Ortho and para positions. If, let us suppose, nucleophilic substitution is there. That kind of examples are very rare in nature. Let us discuss that also. Okay, nucleophile. Nucleophile is electron rich center, and this will not attack ortho and para positions, because ortho and para positions are also electron rich. If you see all these resonating structures, electron rich, ortho, electron rich, para, electron rich, again ortho position. So that nucleophile is also electron rich. It will not attack the electron rich center. It is going to attack that carbon which is slightly electron deficient compared to all these. If you see the remaining positions, there are 1, 2, 3, 4, 5 positions are there. Since 3 positions are already electron rich, this nucleophile is going to choose the other positions except that of substituent and that of 2 ortho and 1 para. So remaining are these two only. So meta position is slightly electron deficient. Here I have not written any electron rich density because of these. I have considered this structure because of these structures only. I have distributed the negative charge in 3 positions. Okay, so that 3 delta negative is balanced by 3 delta positive, which where the oxygen is donated, and that electron density is distributed between 3 positions. 2 of them are ortho and another one is para. Okay, so considering the nucleophile is electron rich center, that will attack only electron deficient center. Here these are electron rich center, it will go to meta position only, since 2 meta positions are equivalent, just like ortho. Ortho have considered as only 1. Okay, so meta will also be only formation product is only 1. So that the nucleophile attack, where the electron donating group present to benzene, electron donating group present to benzene will attack the electrophile to ortho and para position. So electron donating group attached to benzene will direct the incoming electrophile to ortho and para position. So it end up with that reaction end up with the 2 products. One is ortho and the one is para substituted product. Here the electron donating group which directs the incoming nucleophile. If there is a nucleophilic substitution takes place, these type of examples are very rare in nature, but I will tell you. So nucleophilic substitution is there, let us suppose. So what happens is it will direct to meta position, as you can see in this structure. Coming to this structure now, I have taken the resonance structure. Here it is an electron donating resonance, that is minus M effect, because electron donating resonance effect, it's a minus M effect. So that the minus M effect will end up the electrophilic substitution at ortho and para positions, and that minus M effect will end up the nucleophilic substitution at meta position. Now coming to this benzaldehyde example, where it is there is a multiple bond between carbon and oxygen, so that a multiple bond is dragged towards this oxygen. So what happens? Oxygen will get a negative charge, and in order to again balance the valency, if this bond is shifted, only 3 bonds will remain. So in order to balance the valency, this bonded pair is shifted to the carbon of benzene and carbon of aldehyde group, so that there is a double bond. Here what happens? There are 2 electrons are there. If you take 1 electron here to this carbon, and let us suppose we will discuss about this. Here it is a compound where 2 of the electrons are shifted here. One is of oxygen only, another is of this carbon, and if 2 of them, both the electrons will go, what happens? One is already the electron of oxygen, one more is of carbon, so only 1 electron will become the extra, because this electron of oxygen is present on oxygen only, so there is no change in the charge, and this electron of carbon is shifted on oxygen, means oxygen gains only 1 extra electron, and that is -1. So now this carbon becomes a plus. In order to balance the valency, carbon shouldn't have the 3 bonds, it should have 4 bonds, so that this bonded pair where the 1 electron is of C2, another electron is of C1. C1 electron remain on C1 only. C2 electron will go on the carbon containing aldehyde group, so that plus becomes, by gaining 1 electron, it becomes neutralized. So plus 1 by gaining 1 electron becomes neutralized. Okay. Now finally the second carbon has lost its electron, that is what it is gaining the plus. So this structure I have written right over here. You can imagine like that. If you are donating the bonded pair, means there is only 1 electron transfer, because already 1 electron is of that oxygen and 1 electron is of this carbon. So carbon finally gives the electron to oxygen, gains a negative charge, and this carbon again takes the electron of C2, like this one. Again I already told you the positive charge is balanced like this. So this electron of C1 remains with the C1 only, C2 electron will go towards the carbon which contains a aldehyde group. So finally this guy becomes electron deficient, so that I have written the structure like this. This is the starting of the compound, so it goes like this, and the bonded pair is shifted here, so it gets a positive charge. Again, this positive charge has a distribution capacity. Delocalization of electron takes place. So the delocalization of electron from C3, between C3 and C4 will come to C3 and C2. So C4 electron is neutralizes the C2, so that C2 becomes neutralized by gaining the electron of C4. So C4 becomes electron deficient now. So like that, C2, C4 and C6 becomes electron deficient center, if you go like that. So what happens here? The nucleophilic addition takes place very easily. As in case of these, the electrophilic addition takes place very easily, because if you see all these resonating structures, the ortho and para positions are electron rich centers. So electrophilic substitution takes place very easily in this case, because it is an electron donating. Since it is an electron donating, it activates. The ring becomes a negatively charged, let us suppose. So that electrophile easily attacks. Here, the substituent is already electron withdrawing group. So what happens after withdrawing the electrons? This guy becomes electron deficient. So what happens? Nucleophiles are electron rich. They are tending to attack the electron deficient centers. So this is the electron rich guy, and these are electron deficient, as you see all those resonance structures. So electron withdrawing group attached to benzene are having the most affinity towards the nucleophilic substitution, because the electron withdrawing group creates the electron deficient centers across all those ortho and para positions, and making the benzene to easier for the nucleophilic substitution. So nucleophile attacks these positions because this is electron and these are electron deficient. You see all those resonance. So that electron withdrawing group, they show electron withdrawing resonance effect, so that it becomes plus M effect. See here, by donating, I will tell you, see here, by donating these will get a negative, this group will get a positive charge, means this is a plus M effect. Here they take the electron density, that will become minus M effect. Here I am changing the explanation. The first I have taken that as a positive. Here it will take the negative charge. It will take the negative charge, so that it's a minus M effect. Okay, the substituent will here the one key point, electron donating resonance is plus M effect. Electron withdrawing means it gains, the substituent will gain the electron, so that minus M effect. I beg your pardon. I beg the pardon for making that mistake in the previous explanation. It's a plus M effect and this is a minus M effect. Now, here the nucleophile will go to ortho and para position. So, electron withdrawing effect, that is the minus M effect, will direct the nucleophile to ortho and para position. So that nucleophilic substitution will end up with ortho and para products. What if the electrophile is present? What if the electrophile is present? What is electrophile? Electrophile is electron deficient center. Electrophile, the electron deficient center will not attack the electron deficient center only. It will attack that position which is slightly electron rich. Compared to these positions, here there are positive charge means electron deficiency is there. Here no positive charge means compared to these positions, this position at that point of a time act as a nucleophile. So that electrophile attacks that position which is nucleophilic in nature. So compared to these are electron deficient and this seems to be electron rich now. So that electrophilic substitution of those compounds in which electron withdrawing group is there, they have the minus negative mesomeric effect or the negative resonance effect, because electron withdrawing is there. So electron withdrawing, that substituent will get a negative charge. So that nucleophilic addition takes place. Nucleophilic addition, they will direct to ortho and para. Nucleophile negative charge, it attacks to ortho and para. If electron rich deficient center is there, so it is an electrophile. Electrophile will not attack the electrophilic center only. So it will not end up with ortho and para. It goes to meta position. So that remember only one point here, the electron withdrawing group will direct the electrophile to meta position. Okay, so that I have told you already the kind of the information like this one. The withdrawing group, they contain a multiple bond. So lone pair containing are electron donating in nature. So they contain a multiple bond, and they direct the incoming electrophile to meta position. So electron withdrawing group which contains a multiple bond, it directs the electrophile to meta position. Electron withdrawing group, they contain a multiple bond which directs the electrophile to meta position. So finally I will conclude here. Electron withdrawing group will direct the electrophile to meta position, nucleophile to ortho and para position. In a same way, electron donating groups will direct electrophile to ortho and para, opposite to this. Electrophile to ortho and para, and nucleophile to meta position. So this should be your key point in order to solve all those questions.